block, it's a 2-hour block that you're scheduled in. I have 2 2-hour blocks. You're welcome to turn up at both of them, but you must turn up at the one you're in, and you must, I'll explain this again in an email, but I'll be looking for your views on the other people's presentation. Particularly, I'll be asking you to email me with maybe 2 positive things associated with every presentation, and maybe 1 negative. Concentrating on the positive, 2 positive things and negative, in a spirit of constructive criticism. The negative thing can't be, you looked awful, you smell bad. That's not constructive. Be constructively critical, because they will be doing the same to you. Be nice to them. And that you found maybe that might be able to happen in the future. And then positive things as well. Okay? You'll be required to do that. If you don't do that, I won't be giving you marks for your presentation. Part of this process, part of the way to do good presentations is to watch other people do good presentations or bad presentations, and to form an opinion about what made it good or what made it bad. That's how you learn, partly how you learn to do good presentations, if you're watching other people and watching them not just passively, but watching them actively and trying to assess, why was that good, why wasn't it good. And once you can see other people making mistakes, and once you can see other people doing it well, you learn how to do it. So that's the reason I'm going to ask you to do that. I'm not asking you to do my job for me, I'll be marking them as well. But this is for you to learn. That makes sense? I should put all this in an email. A lot of stuff we covered just now. I'll put it all in an email to you know. Just any questions about any of this? CYM, Connor, Craig, Palav, a few others there. Palav has a chat for me. Yes, we can talk offline later on, no problem. Any other questions over in NUIM? Any questions? Oh yeah, questions. Ready to test, yes? Another good question, thank you for that. So the question is, NUIM, the format of the class test on Friday. It's another thing I meant not to about in my list of things, I forgot, so thank you for the reminder. Class test on Friday, some people have been emailing me with worried emails looking at past exam papers in this topic. You'll notice the past exam papers date back from about 2009, 2008. That's quite a long time ago. This module changed about 4 years ago to its present format. So those exam papers are old and they represent an old syllabus. The syllabus has changed. So in particular, in the exam questions, you will find question 1. It talks about queuing theory. Queuing theory is very interesting, very useful for people studying communications engineering. It's all about the queues form, the average waiting time for queues. So very important for setting up a communications network, for example. We don't cover it in this module anymore. It gets covered later in the ICE, Information Communications Engineering program. Okay? Because that's where it's most directly at. We don't cover that anymore. So question 1 shouldn't make any sense to you. So don't be worried if it doesn't. As regards the class test, there should be a mixture of a number of things. There will be simple questions, basically giving you some data and asking you to apply an algorithm. Okay? Here's some data, here's a function, applying using that bisection. Here's a function, with numerical integration. Here's a function, here's an ODE, do a couple of solution steps. So easy to solve. So they're pretty easy, and I expect people to get them right, so you can pass the module. Okay? They don't require a huge amount of understanding, they require your ability to do basic arithmetic. There'll be a few of those. That's the test where you just be paying attention to all the lesson. In addition to those, there will be more complicated questions, more nuanced questions, to derive this, to derive that, explain why this is better than the other. Okay? They'll require more thorough understanding of error analysis and all that stuff. As I said several times in this course, a lot of the assignments, you could do them in a single slide. But for some reason, I've been working on for 3 hours with 99 other slides. So the 99 other slides are what's important. It's what makes that one slide work. Okay? You need to understand all that stuff in those other slides. The background, the motivation, the error analysis, all that kind of stuff. Okay? I shan't give you anything terribly difficult. Some of the derivations we did are maybe 4 or 5 slides long. I wouldn't expect you to memorize those, but I might jump in halfway through one of those and ask you to fill in a step. We'll see after that. You will be expected to know that kind of derivation stuff and that theory stuff. And then finally, the question is about MATLAB, whether you'd be asked to use a MATLAB. And what I would probably do is ask you to maybe write a little MATLAB fragment, or maybe I might give you a MATLAB fragment and ask you to comment on it. Thinking about maybe making some MATLAB fragments without mistakes in so errors. You don't need to spot the errors, for example. Or giving you some MATLAB code and ask you to comment on how to make it better. Something like that. And then I have to write it. So there are the three components. One is very simple arithmetic, just applying these algorithms. Two is the important part, is understanding all these algorithms. And then three is the implementational aspect, a piece of MATLAB code or pseudocode. It isn't MATLAB code, but an algorithm of some sort written by either MATLAB or C or something like that. And you're going to have to identify, modify it, maybe identify aspects of it or something. Any more questions? They're good questions. Anyway, any questions over there? You heard the answer to that, did you, hopefully? Any more questions here? You see? Okay, so let's crack on. I want to finish this handout today. In fact, I'm not going to finish this handout today, but we'll get through as much of it as we can. And I want to, usual format, what we'll do is we'll do the slides and then we'll take a break and then we'll do a little bit of MATLAB, okay? And we'll show you. We'll do the theory first of all in class, and then I've got some MATLAB code which I'll make available for you on the website later on. I will go through the MATLAB code and see how to implement this stuff. Okay? So last Friday, we started talking about partial differential equations, and we realized that partial differential equations are much more complicated than ordinary differential equations. In ODEs, we've a physical quantity, such as the angular displacement of a weight on a string, there on the left, or the voltage at a point in a circuit on the right. And so we have an interesting physical quantity, and it depends on a single variable. So in both of these cases, it depends just on time. So the pendulum swings back and forth with time, and its angle changes with time. And over here, the voltage at node B changes with time. But that's all they depend on. They don't depend on anything else. Okay? The voltage at node B doesn't depend on location, for example. So as long as it's anywhere between this end of the capacitor and this end of the resistor, we assume at low frequencies all these voltages on the right are the same. So there's no spatial dependence. That's actually an approximation. There actually is a spatial dependence, especially at higher frequencies, as you have seen in electromagnetics. But in simple circuit analysis, we assume that it's on a single variable and it just varies with time. So they're tricky to solve, and we looked at ways of solving those. Partial differential equations are even more tricky because now we get physical quantities that vary not with a single independent variable, maybe 2 or 3 or 4. So on the right-hand side here, we have a picture of the power distribution we have of a wireless system. We have a mast over here on the left. It's spewing out magnetic waves, which are bouncing off the mountains and deflecting around the edges and doing all sorts of stuff. And the power decays as you move away from the transmitter. So we go from orange and red, meaning high power over here, to green and blue, meaning low power. But as well as decaying with distance, we have all these local effects caused by shadowing and diffraction and all these. And to explain, to solve this, so we have an interesting quantity called power, and it varies, in this case, in 2 directions, 2 independent variables. One spatial variable, the x direction, and one spatial variable, the y direction. Okay, so horizontally and vertically. So it varies in 2 dimensions. Okay, so it's more complicated. In fact, this is a 2D approximation. In the physical world, it varies in 3 dimensions. So in the z direction as well. It also depends on time. In the physical world, it's even more complicated. It would actually be 3 spatial dimensions and a time dimension. But in this computation, we just assume 2. We assume time is harmonic time dependence, and we assume things don't change in the z-axis. So it makes it easier to do, and you can solve it then on a computer in realistic time. Similarly, on the left is a picture with electromagnetic waves bouncing off a plane, and again we see a similar thing. The waves depend on vary in the x, y, z direction and with time. So we would classify this. We did on this last Friday. We've got three different types of equations we want to look at, and they can be written in a general form as the following. They're second order PDEs, so we have some unknown quantity u. It varies either in the analysis we will be doing, we're going to assume it either varies in two spatial dimensions, so x and y, or perhaps it varies in one spatial dimension x and one temporal dimension time t. Okay? So again, we're going to restrict ourselves to simple cases of two-dimensional or functions of two dimensions. Physical problems are typically functions of 4, x, y, z, and t. That just makes things too complicated without necessarily helping us very much. So we'll keep it either a function of two spatial dimensions or one spatial and one time. So two independent variables in both cases. And in all cases, it's a second order PDE, so second order derivatives. And we can write them all in a general form as a times the second derivative of u plus 2 times b times the second derivative of u, once with x, once with y, and plus c times the second derivative of u with respect to y. All the second derivatives on the left, and on the right-hand side with a whole bunch of terms in x and y, in terms of u itself, in terms of the first derivative with respect to x, and the first derivative with respect to y. And then alternatively, if we're considering a different kind of physical system where we're looking at a function of one spatial dimension and time, is exactly the same, but instead of differentiation with respect to y, with differentiation with respect to t. Okay? And this is the general form. So this is like an ODE. In an ODE we had df, or we had dy dx equals some function f on the right hand side. Here we have a collection of partial derivatives equals some function f on the right hand side. So it's like a generalization of the ODE idea. And we can categorize these depending on the values of a, b, and c. So the reason we write it in this form is because then we can find out something about what solution mechanism to use. So if these values a, b, and c are such that ac minus b squared is positive, it's an elliptic partial differential equation. So the Laplace equation, which we covered in the earlier slides last Friday, is of this form here. We have an unknown quantity u, often turns up in electrostatic, so u might be an electric field, varies in the x direction and the y direction. And to be a proper electrostatic field, it has to satisfy the second derivative in the x direction plus the second derivative in the y direction equals 0. Okay, so we can get no charge. So we get Laplace's equation. And so this is of the form of the previous page, where a is equal to 1, b is equal to 0, and c is equal to 1. And we get ac minus b squared is consequently equal to 1, which is positive, and this is elliptic. Okay? If this determinant is equal to 0, we call it a parabolic equation. So the diffusion equation governs heat flow along one dimension, for example, so a long, thin bar of metal, for example. And we have quantity u here, is maybe the heat content, and its second derivative with respect to x is equal to minus its first derivative with respect to t. Okay? So this is of the form, the general form, where a is equal to 1, b is equal to 0, and c is equal to 0 as well. And on the right-hand side, we have f is minus ut. Okay? So in this case, we've got ac minus b squared is 0, and we say this is the parabolic equation. And then finally, if ac minus b squared is less than 0, there's a typo in these notes on Friday. I've changed them since. There's a fresh batch up on the website you can download. So this typo has been corrected. So if this is less than 0, we call it a hyperbolic equation. So the wave equation, which governs the wave action along a guitar string or vibrations on a guitar string, for example, where u would be the displacement of the guitar string from the horizontal. As you pull a string back, it vibrates around a horizontal resting position. and its displacement is given by u, and its second derivative in x is equal to its second derivative at the time. So in other words, uxx minus utt is equal to 0. That's of the general form where a is 1, b is 0, and c is 1, minus 1 rather. And the determinant is consequently 0, and this is hyperbolic. What's the purpose of all these terms, all this terminology? The purpose of all this terminology is because we can now classify partial differential equations into these 3 different types. And these 3 different types of equations have 3 different types of ways to solve them. Okay? So I've given an example of a hyperbolic equation, the wave equation, but there are many others that turn up in physics and engineering. I've given an example of a parabolic equation, the heat diffusion equation, but there are many others as well, which are also parabolic. Okay? And in fact, that nice picture I had at the start, where was it, of the power propagating over the mountainous terrain profile. This is actually an example of a parabolic equation as well. Or the way you can solve it is a parabolic equation. It's actually an elliptic equation, but you can approximate it as a parabolic equation, which makes it easier to solve. So not just for heat diffusion, but in this case for propagation of electromagnetic power can also be expressed as a parabolic equation. And similarly, the elliptic equation, we gave one example of it, but there are many other examples as well. So these are classes of equations, whole families of equations. It's worthwhile to put some efforts into finding solution mechanisms for these classes, because then they can be applied to a whole wide range of different engineering problems which happen to be in that class. So let's look, or let's revise what we did, ways to solve the parabolic equation. Where's my nice picture? Parabolic equation is an example of an initial value problem. Let's just go straight to where we had the statement of the problem. Okay, so for a diffusion equation, let's imagine the constant diffusion coefficient. So let's imagine a situation where the diffusion coefficient is constant. It does not vary with space. So in other words, we have a homogeneous material. If it wasn't homogeneous, the diffusion coefficient would be changing because there would be different types of material as we travel along the x-axis. Let's assume it's all made of the same type of material as we go along. So d is constant. And if d is going to be constant, we might as well set it equal to 1. And let's assume we want to solve this equation for x values between 0 and 1, again, just to make life easy. More generally, you might want to solve it between a and b, but just to make things, the notation a little bit easier, we'll say it's between 0 and 1. So our initial value PDE equation becomes ut, for the first derivative of u with respect to time is equal to the second derivative of u with respect to x. Okay. So u is some function of x and t. We don't know what it is. But we are told that whatever the function is, whatever u is a function of x and t. And if you take a derivative of it with respect to t, you get exactly the same as you would get taking a derivative of it with respect to 2 derivatives of it with respect to x at every point. We have this balance between the time differentiation and the second order spatial differentiation. So we don't know what u is, but our challenge is to find the u that when differentiations, this balance is achieved. In order to help us, we're given some initial conditions. We're told at time t equals 0, so at the start of our simulation, we're given the value of u everywhere, all values of x between 0 and 1. So we're given the answer, but only for time t equals 0. We're not given it for time t equals 1 or 2 or 3, only for time t equals 0. So we need to use this to get the answer for time equals 1, 2, 3. We're also given boundary conditions. So for any value of t, we're given the value of u up to 2 endpoints, u and 0, x equals 0 and x equals 0. We're not given the values at the interior, but at the 2 exterior points we are given those. And I've updated this from Friday as well because make it a little bit more general. Generally, the left-hand boundary condition is that the leftmost point, x equals 0, is held, its value equals some known function g0, where g0 is known. Similarly, the right-hand point, any value of t is equal to some value, some function g1t. In our example later on, we'll assume these are constants. So in other words, the 2 boundary conditions are held at constant values. Okay? But more generally, there could be time-invariant values to make it even more complicated. Okay. An explicit solution scheme takes the equation ut is equal to uxx, and we discretize in time and space. So we say this is a first order derivative with respect to t on the left, we have a second order derivative with respect to x on the right, and we say let's take our spatial dimension, x between 0 and 1, and divide it up into lots of these little nodes. So this is the kind of thing we've done before. All these little points, xn plus 1 is equal to the previous 1 plus h. So x0 is equal to 0, xn, capital N is equal to 1, so there's n plus 1 of these points and they're separated by h. We discretize in the spatial dimension. We also discretize in the time dimension. So we start off at time t is equal to 0, and we next solve at time t is equal to k, and then 2k and 3k and 4k. Okay, so the time step is equal to k. So at time step I plus 1, the time value is equal to time at step I plus a further infinitive k, which is expressed in seconds. So we now have discretized space, we've discretized time, so consequently the left-hand side here is a derivative with respect to time, and we know therefore that if uni is the value of the unknown u at spatial location n and at time step I, that's what this notation means. Uni means the value of the unknown function at spatial point n, xn, and at time step I, so ti, that's what the little double notation means. You can work out the temporal derivative by doing a forward difference approximation. We can say un at time step I plus 1 minus un at time step I divided by the time step, which is k. So this is just on the left-hand side. At the bottom here, we have a first order forward difference approximation for the time derivative. Okay? So we have an unknown u. We look at its value at a particular point n. We look at its value at time t is equal to ti plus 1. We look at its value at ti, get the difference, see how much it's changed in that time step, divided by k. We don't know what these values are yet, but we're going to rearrange them and find a way of solving them. On the right-hand side, we have a second order differentiation with respect to x, and we can do that by doing a central difference approximation, as we saw in our handout on numerical differentiation. Second order differentiation in the spatial difference, we take a particular time step I, so we're interested at time step I, the second order derivative in space is equal to, well, we take the value of u at spatial step n, we look at the value of u at n plus 1 and at spatial step n minus 1, add those two together and take away twice the value of u at spatial step n. We divide that by h squared, where h is the space. This is just a central difference approximation to the second order derivative. We cover that way back there. So we've gone from a continuous function, or a continuous partial differential equation, to a discretized system here. So up here, the very top equation is for some function u we would like to solve. We can't solve exactly for u, so instead we content ourselves with discretizing u at a finite number of points in space, and for each of these points in space at a finite number of points in time. So we have a finite collection of points here that we're going to try and work out, and that's going to be our discretized solution to u. We need to find these u's. How do we find them? Well, we can rearrange, well, a picture. Here's a picture. So every row here corresponds to a particular time step. So at the bottom row, we've got time I is equal to 0. So it corresponds to t0. Usually t is equal to 0, at the initial time. And these are all these dots refer to individual discretizations along in the spatial dimension, going from x0, which is to xn, which is 1. Okay, so all these dots here along a row correspond to, for a given instant of time, the spatial, or the values of u at different spatial discretizations. Going vertically, we have all the different time steps. So for a vertical column here, this represents the value of u for a particular spatial location for different version or different points in time. So this point here on the bottom row is equal to the value or represents the value of u at time step 0. Travel up 1, we get the same spatial point, but now it's its value at time step 1, time step 2, time step 3, and so on. That's what that means. It's a two-dimensional representation of the problem we have to solve. We have to find the values associated with all these dots. Okay, we have to do. Now the initial conditions, remember the statement of our PDE told us that at time t equals 0, we are given the value of u for all the points along the spatial domain. So we're given the value of u for time t equals 0 for all of these points. So the green points here are all given to us. We have them available to us. So these numbers are given. We're also given the boundary conditions. So at the leftmost point, spatial point, and the rightmost spatial point, we are given the value of u no matter what time step. So all these orange points on the left column and the right column represent known values of u at the two extreme boundary locations, regardless of time. So the green ones were given, the orange ones were given. The blank ones were not given, and our job is to come up with a piece or an algorithm that can fill in these values. Okay, that's the challenge we have. So how do we do it? Well, this is our discretized version of the partial differential equation. And we are at step I, so we can assume, time step I, so we can assume we've filled in all of these circles up as far as time step I for some value of I. And we would now like to fill in the circles for time step I plus 1. So this is the next row above. So we assume we have this is a given step in the middle of our algorithm. We have all the values up as far as I. We'd like to get to I plus 1. Well, what we do is we take everything with an I and put it on the right-hand side, and everything with an I plus 1 and put it on the left-hand side. And when you do that, but on the left-hand side here we have minus uni, so we take him to the right. We multiply across by k, and we get this equation in the middle here. And this equation is nice because it tells us that, if you can see it, it tells us that the value of u at spatial point n at time I plus 1 depends on the value of u at spatial point n at time step I, and also its neighboring points, un plus 1 and un minus 1, also at time step I. So if you have all the values at time step I, we can combine them in this way and start getting values for time step I plus 1. And this is how we systematically solve. Stability, and we'll see this in a MATLAB example, for stability we require that this thing OR, which happens to be the ratio of k over h squared, if you follow in the couple of steps between the top equation and the middle equation, OR is k over h squared, has to be less than a half. Okay? So this has to be less than a half. If it isn't less than a half, repeated application of this updating process will cause the solution to diverge. If you keep it under the half, you have a good chance of keeping it stable. Okay? Why is that? You can see this 1 minus 2r here. So when r gets greater than a half, it becomes negative. Okay? So you end up introducing oscillations. Simplified explanation. So that's broadly speaking. You can see r is equal to a half, hence this term disappearing, this contribution disappearing. More detailed explanation. That's a good. Now, so this tells us that provided we have all the values in row I, time step I, we can now work out all the values in time step I plus 1. And it's an explicit method because we can just, it's a systematic method, we can systematically just fill in row I plus 1, circle after circle after circle, very easily. So it's an explicit method. We'll see an implicit method later on to see what the difference is. The stability condition is a bit of a kicker because you got to keep h small. H is your spatial discretization, and you got to make that small because, as we saw, the smaller your h discretization, the more accurately you are modeling the derivative. So you got to keep h small in order to accurately model the derivative, the spatial second-order derivative. So if h is going to be small, well, therefore k must be very small because remember, r is, what was it? k over h squared has to be less than a half. So if h is small, k must be very small to meet this. That means that you have to take very small time steps. So you might want to model this process, this equation, for a long amount of time, from time t equals 0 to t equals 100. But in order to keep stable, you've got to take very small time steps. Small time steps which are smaller than would be strictly necessary to get the numerical differentiation right. You can get the numerical differentiation right with a certain time step, but you have to make it even smaller than that again in order to get it stable. And that's a bit of a drawback. Here's a little diagram of what this updating process means. You have time step I. You have these dots are given to you. You've filled them in already in the process. And now to fill in the blank circle in time step I plus 1, we have a contribution from the spatial step n directly below it, and also a contribution from spatial point n minus 1 and spatial point n plus 1. So let's go back to our little diagram here and see systematically how this would work. We would start off on the bottom row here at t is equal to 0, and we'd have all these values. These values are given to us by the initial condition. So then we would go to time step I is equal to 1, and we would go to the leftmost point. And we would see the leftmost point is an orange circle. He's a boundary condition. We then go over to the next point, which is a blank circle. We don't have him, but our update process tells us that a combination of the first orange dot on the bottom row plus the first green circle on the bottom row plus the second green circle in the bottom row combined together can give us an estimate for the first blank circle on this row, in row 1. We can fill him in. Then we can go to the second circle and use the first 3 green circles below to fill him in, and so on and so forth. We step all the way through from left to right until we get to the second boundary condition. And hey presto, we've filled in time step I is equal to 1. Then you can go to time step I is equal to 2, and then I equals 3, and as much as you want. Okay? So we'll look at some MATLAB code that does that later on. Now, a problem with that explicit scheme is you have to make a very small time step. Let's do something a little bit better, a little bit more complicated, called the Planck-Nicholson scheme. And the Planck-Nicholson scheme says we have to get a spatial difference. Okay, so our equation requires uxx. Let's go back to our little picture here. Okay, so at any given step, we're trying to go from time step I to time step I plus 1. And we have to discretize in space. And in the explicit scheme, what we said was, well, we compute uxx, the second derivative in space, based on the values at time step I. So we take 3 neighboring values at time step I, and combine those to make a central difference. But actually what we need is values of the central difference, not just at time step I, but throughout the entire region between time step I and time step I plus 1. So this is like the Euler versus the predictor corrector. In the Euler method, we just took values at the start of the interval. But the predictor corrector said, let's take values at the start and at the end. So the Planck-Nicholson says, rather than just computing uxx based at time step I, let's also compute it at time step I plus 1, which we don't know yet, but let's write it down what it is in terms of these unknown values. And let's average uxx based on both of those. So let's see what that would look like. So Planck-Nicholson did that. So the left-hand side remains the same. The time derivative is computed in the same manner as before. But on the right-hand side, we have 2 terms now. The first term is the central difference approximation to uxx based at time I. So it involves spatial step n plus 1, n minus 1, and usual central differencing. The second term is the central difference computed at temporal step I plus 1. Okay. Because uxx is needed throughout that entire transition from time step I to I plus 1, so why would you just use values at time step I? They're no better than values at the end of that time step. Let's use the values at the end of the time step as well. Problem is, values at the end of the time step aren't known yet. but we can write them down and play with them. See what happens. Let's play with that. We can rearrange that. We can put all the terms involving time step I plus 1 to the left, so the unknown terms on the left, and the terms involving time step I, which are the known terms, go on the right. And OR is the same as before. It's k over h squared. We get this. This is our equation. And there's a problem now because it's no longer explicit. First time we did it, it was nice because on the left-hand side, we had un at time step I plus 1, given explicitly in terms of previous values. Now, un at time step I plus 1, which is the first term here, is given in terms of, on the right-hand side, previous values, but also depends on its neighboring spatial points at time step I plus 1. And the problem is we don't know these. We can't get un I plus 1 because we don't know its neighboring values. I can't get its neighboring values because we could write an equivalent equation for them, which would require knowledge at un I plus 1. So there's a chicken and egg problem here on the left. These values on the left are all interacting with each other and defining each other, but we don't know them. We can't disentangle them. But we can't disentangle them explicitly, but what we can do, and here's our little picture, here we have time step I plus 1 is the upper row here. The center dot, the center blank dot is un I plus 1. And we see he now depends on the 3 red dots below, which are known, the values at un and the neighbors at the previous time step. But it also depends on the values of its neighbors at this time step. And they're not known yet. They're not known. So this might be a better method because we're not just taking spatial derivatives at time step I, we're taking spatial derivatives throughout the entire time step. But the problem is we're now a little bit tangled up. So how can we disentangle ourselves? So the left-hand side of the equation are unknown, the right-hand side are known. So we can disentangle it as follows. We can write down a linear equation in 3 unknowns. So for position n, on the left-hand side, we have the unknowns correspond to n plus 1, and n minus 1. And we have n plus 1 spatial samples that we have to solve for at time step I plus 1. But only n minus 1 of those are unknown. The 2 boundary points are known. So there's n plus 1 discretizations, but 2 of them are known. So we've got n minus 1 numbers of the form un I plus 1 we've got to work out. And they're all bound together with their 2 neighbors. We can write a sequence of equations for spatial point 1, 2, 3, 4 up as far as n minus 1. We can write a sequence of equations and we can solve it using a matrix equation. We shall see how we do that now. Let's write out what we want to do. So here's our problem. This is our implicit discretization scheme. So the quantities on the left are unknown, the quantities on the right are known. So if n is equal to 0, the leftmost discretization, we needn't bother. That's a boundary condition. We don't have to solve for that. It's given. If n equals 1, which is the first blank empty circle on row I plus 1, the equation at the top there, we put in n is equal to 1, you get this. Okay? And we have an equation involving u1, u2, and u0. u0 is a boundary condition, so he can go over to the right-hand side. And we're left with an equation in terms of u1 and u2. Everything on the left here is unknown, everything on the right is known. And the combination of a previous time step or a boundary condition. For n equals 2, we're at the second empty circle in our row, in our new row I plus 1. N equals 2, putting into this equation at the top, we have an equation for u2 at time step I plus 1 involving u3 and u1. u3 and u1 are both unknown. We don't know them. We have an equation for u1 above here, and u1 also appears here. So these are coupled equations. We can't find out u1 until we solve this equation. We can't find u2 until we solve this equation. They're bound together. We can keep on going for n equals 3, n equals 4, n equals 5. In general, up as far as n minus 2, we can write that. For n minus 1, we get this. And we see the first term here is U capital N. That's a boundary condition, so that one is known at the boundary point, so he can go over to the right-hand side. So we end up with n minus 1 equations with n minus 1 unknowns. As for n is equal to 0 and n is equal to n, the boundary condition. So we know that. So n minus 1 equations and n minus 1 unknowns, and that can be written as a matrix equation. Okay. So the system of equations I just wrote down there, study them, print out the notes, got a cup of tea, got a pen and paper out, and convince yourself that this matrix equation is identical to the system of equations we just went through there. So this is a matrix equation. This vector here are the unknown quantities, are the blank circles at row I plus 1, U1, U2, U3 up as far as UN minus 1. And we see, for example, the first equation, Ui plus 1, when you do this matrix multiplication, you get 2 plus 2r times the first element in this vector, minus r times the second element, U2. And that corresponds to our first equation here, which was 2 plus 2r times U1 minus r times U2. So these coefficients here, 2 plus 2r and minus r, are the first two coefficients in our matrix. Everything else is 0. For the second equation, involving spatial step 2, spatial point 2, our coefficients on the left-hand side were 2 plus 2r multiplying U2 and minus r multiplying U3 and U1. And we see in our matrix with minus r multiplying U1, minus r multiplying U3, and 2 plus 2r multiplying U2. So what we end up is this banded tridiagonal system. It's a matrix where we only have non-zero numbers along the diagonal and one diagonal off the main diagonal. Because these unknowns here are only linked to their immediate neighbors, one before and one after. So hence, we only have the main diagonal is a contribution to itself, and the off diagonal is either two neighboring contributions. Everything else is in. It's a sparse matrix. This here, you've got to convince yourself, represents the system of equations we just wrote down. The right-hand side is a vector u. I wrote it here as just a vector, but I couldn't fit it in otherwise. And it looks like this. Ui is equal to the right-hand side of all these equations that we derived. So let's convince ourselves of that. The first equation we derived, the right-hand side, was 2 minus 2r times u1i plus r times all this stuff here. And we see, hopefully I got it right, 2 minus 2r u1 plus r times r. So these are just the right-hand sides of that system, those equations that we went through and derived the two. And they're all lumped together. We have a matrix equation. On the right-hand side, we have known quantities. They're known. They either refer to field values at the previous time step, which we know, or boundary values, u0 and un. So everything in this right-hand side vector is known. You can put a number. So this is just a vector full of numbers. The matrix is a matrix full of numbers. R is the ratio k over h squared, where k is the time step, h is the spatial step. But this is just a bunch of numbers. This vector here is unknown. We don't know this. But it corresponds to the values at, let me find my nice picture, for any given step, I plus 1. It corresponds to all the blank circles in the I plus 1 range. And by solving this matrix equation, we can work out all of these values all at once. So we solve this matrix equation by inversion, or if it's a very big matrix, you have to use some other technique, which I was hoping to cover in my last handout, but you're not going to have time to cover now. That's okay. You can read about it yourself. So you solve that, and that enables you to work out all of these values here in this unknown vector to become known, and then you can fill in all of those circles and then move on to time step I plus 2, time step I plus 2. What I propose to do in 5 minutes, and I will set up a laptop and I'll show you a MATLAB example of this happening. So this is hard to get your head around, just look at mathematics. So I'll show you some code to do it, and hopefully then it'll make a little bit more sense. Should Okay, so let's get cracking again. There. So what I'm going to do is I'm going to do okay, so what I'm going to do is show you some code, first of all, to do the explicit scheme and to show you why you need to obey the stability criterion, and then we'll have a look at the Crank-Nicholas and the explicit scheme. Okay, so let's remind ourselves our problem was, before I do that, checking anyway, so what I'm going to do is just revise this slide very quickly, and then I'll boot up MATLAB. Well, I have it open. I'll do desktop sharing. We'll have a look at a MATLAB code and see how to do this. So the explicit scheme was nice because it told us that for a given unknown value, un at time step I plus 1, so the leftmost side of the top equation there, which is the, in terms of our diagram, it's the circle, the blank circle in row I plus 1. And it told us that provided we had values at time step I, the previous time step, we could combine them together via the equation on the right-hand side. So basically we're taking the 3 red dots and we're combining them according to that equation to get the unknown circle. Okay. So, and it's a explicit scheme because once we have all the values at time step I, we can just combine them for any given point in time step I plus 1. And the values in time step I plus 1 are independent of each other. You can get spatial point n without regard to spatial point n plus 1 or n minus 1. So it becomes this a process of systematically stepping through all the spatial discretizations in time step I plus 1 and just updating them according to that formula. Let's have a look at some MATLAB. Do this. previous time step. That's 1 minus 2r times the value at the point in question. That gives us u value new. We had u value old, we make the updated one, and then we overwrite. So u value old becomes what we have in u value new once that's all finished, and we keep on iterating. And then once we get into this loop again with plot x u value old, this will now be the updated value of u value old, and so on and so forth. Okay. Let's run this thing and see what it does. Before I do that, let's have a quick think. I think it's a good idea. Where's our equation? Our equation is ut is equal to uxx, okay? So we're going to see a bunch of pictures here. On the x-axis is the unknown values, the samples from 0 to 1, and the y-axis is the value of u. The very first frame, u0 will be 10, everything else 0. It corresponds to an impulse being injected into the leftmost point. So you can imagine an iron bar and an injecting piece. The very first frame, very leftmost point will be 10, everything else 0. For the next frame, the next frame, the next frame, that heat will diffuse its way through, and we'll see the value of u vary with time. What will the steady state result be? So the equation is u, the derivative of u with respect to t at a point is equal to its second derivative with respect to x. So the steady state solution is when it doesn't change anymore with respect to time. So the time derivative is equal to 0. Okay, so ut will be equal to 0 in the steady state. So once this runs for a long time, it will reach steady state. It won't change anymore. It won't change anymore, so u underscore t will be equal to 0. U underscore t is equal to 0. What shape will you have on anybody's hand? This is just to see if anybody managed to stay awake for 20 seconds. Anyhow, look at that equation. If u underscore t, if the first derivative with respect to time is equal to 0, our steady state equation is u is some function of x, whose second derivative is equal to 0. What kind of function has a second derivative equal to 0? Well, yeah. So in steady state, in the initial stages of this animation, we're not in steady state. And u is changing with respect to time, as you can see. But in the steady state, it settles down, it stops changing. The animation stops changing from frame to frame. And that corresponds to u underscore t is equal to 0, no longer changing. If u underscore t is equal to 0, it means our equation is, the steady state equation is u underscore xx, the second derivative of u with respect to x is 0. So the question is, what kind of function u has that property? And the answer given here is, well, a linear function. So a linear function, a straight line function, its first derivative is a constant, its second derivative is 0. So what we expect to see in this animation when we run it is the very first frame will have peak value of 10 over on the left-hand side, 0 everywhere else. The other values will begin to evolve and change as time ticks on, and it will eventually get to a stage where we have a straight line distribution of u across x equals 0 to 1. At which point the rate of evolution will slow down to changes upward long term. So it's always good, the reason I asked you that, it's always good to think about what you expect to see before you see it. Okay, we're very passive these days, I'm as bad as anybody else. The world is great and the internet is great, and we can click on this and we can download that and we can run this and we can play with that. And what it's done is we turned this all into very, very passive. We check and we look at it. The best way of learning about something is before you click, before you run it, before you do anything, you take 5 minutes and you ask yourself some questions. What am I to see? And if you get it horribly wrong, big deal. You've only asked yourself. And if you get it right, it means you've learned something. So that's my little piece of advice to you. If you're ever looking at something like this, if you ever download code, if you ever get something, don't just run it. Take 30 seconds, ask yourself, what do I expect to see here from my understanding? Then see, is your expectation met? If it is met, well done, it means you're learning something. If it isn't met, you're wrong, you're wrong. means you'll be right next time. Okay, that's this little pep talk. Let's run this code. So and see what happens. That'd be great. Running well on my computer, but it's the internet is a bit slow. What's happening here? You can't see it very well because in on the server. What's happened here? I'll run it again. We started off with at the leftmost point 0. The output was 10. U was 10, and everywhere else was 0. And what we're seeing here, it's a bit jerky in your screen because I'm showing lots of frames and the server can't show everything. What's happening is we're getting a smooth evolution from that initial point where it's 10 at the left, 0 everywhere else, and it's spreading slowly, diffusing, hence the name diffusion equation, from left to right. And by the end of the animation, once we go t is equal to 10, here's our distribution of u. We have still, the boundary conditions are still being met. It's still 10 on the left-hand side, still 0 on the right-hand side. They're boundary conditions. They never change. But the interior points between 0 and 1, they all started off at 0, but they've all risen. And they've risen and they've settled down into a steady state behavior, which was, as our friend here suggested, straight line, a linear behavior. So the steady state behavior is linear. So that's a long-term study. In the initial phase, it says it's not linear because there is a time. Let's run it again. Hopefully the server can manage. Out of memory. Oh my God. Run it again. Complain about that memory, but still running with thinking. Picture. At the initial stages, we see a very sharp spike on the left. All the heat is over on the left at that boundary condition, equal to 10. Everything else we have nothing at the moment. I did run it on my Apple, but this is an older computer, so I'm going to just make this a little bit less onerous. We think 10, n is equal to 10 instead. Mr. How do I run the first? That's not that bad. Okay, we'll try it again. Hopefully it works this time. I'm going to give you this code anyway, so you can run it yourself. So it's the animation working there, okay? So again, we start off, value is equal to 10 at the left, equal to 0 at the right, equal to 0 everywhere else. And as the time wears on, that initial input of heat diffuses throughout the region 0 to 1. We end up with a steady state like this. Let's run it again, and this time see what happens if we try and break it. So our analysis told us that we had to make R less than a half. What happens if R is not less than a half? Let's make R 0.52. Okay, so R is now greater than a half. What do you think is going to happen? It's going to be unstable. Let's see what unstable means. Running it again. What happens? We're sort of getting selected frames from this animation. There's the movie of it now. These are the frames in by one. We're getting these oscillations creeping in. We're not hitting a nice steady state of a straight line. It shows that we got a little bit lazy. We weren't patient. For this explicit method, we should have chosen a time step such that k over h squared is less than a half. We chose one such that k over h squared is greater than a half. It's equal to 0.52. It's only slightly greater than a half. This is the answer we get at the end. That's just to show you the need to obey that explicit stability. If you don't obey it, you get very bad answers. That was even for 0.52. If you make it very big, if you make it 0.9, stand back from the computer and catch fire. Not so much. So again, this is for R is equal to 0.9. We get these oscillations creeping in. T in this case is small enough to capture the temporal derivative of phase, small enough to do that finite difference. And the problem is in the stability. The algorithm itself is not stable. The time step in T has to be really small for stability. Let's look at the Crank-Nicholson method instead. Any questions about that before we leave it? Beyond the website tonight, you can download it and have a look at it yourself today and play around. Stick in different initial conditions, stick in different values of R and see what happens. Okay. Anyway, any questions over there? Sorry, that puts a bit of a strain on the server, but I could see what you could see. Hopefully, it's a little bit patchy over the big blue button, but the codes are on the website. You can run it yourself later on. Okay. Let's have a look at something else. Let's open Crank-Nicholson. So the Crank-Nicholson method we just saw is another way of solving this diffusion equation, but it's an implicit method. Rather than going to row I plus 1 and sequentially filling in those circles one after the other, each of them independently of each other, we see that they are linked together. The value at any one little circle on row I plus 1 is linked to the value at its neighbors. And we cannot solve for any one independently. We have to solve for all of them at the same time because they're all linked together. We cannot solve for just one. And we do that by defining a matrix equation. What's the matrix equation? Analysis there, and end up with n minus 1 equations, and n minus 1 unknowns. End up with a big matrix equation coming up now in effect. This is it. Okay. So at every time step, we must make this matrix equation, and we got to solve it. Okay. We're going to make this matrix equation, and make the matrix on the left. We're going to make the vector on the right. We're going to invert the matrix to get the unknown values for all the unknown nodes at time step I plus 1. How do we do that? Well, it's the same as before. Here's the code. Um, 0 to 1 is all the initial stuff. We'll choose delta t is equal to 0.5. We'll change him in a second because we don't have the stability constraint anymore. So we don't need or being less than a half anymore. We can make or whatever value we want. Same old stuff as before. I won't go through all that. It's the same as before. What we do though at this stage is here we're stepping through time. And for time is equal to 0, delta t to upper t. So from 0 to 10, we plot the initial, we plot the value of u value old. But this time, rather than stepping through and filling up u value point by point, we make a right-hand side vector. Okay, so for all the interior nodes, 2 to n, we make the right-hand side vector. The bold ui here, which is given on this slide. So we make all these numbers. These numbers are all available to us. They're all in terms of u values at the previous time step. We fill all those in. So it's up to you to look at the MATLAB code and check it against the PDF and see what it's saying. For the boundary values, are the nodes beside the boundary values are a little bit different because we have boundary values involved. So again, for the first interior node and the last interior node, the form is a little bit different. There's an extra term in terms of u0 and un, which are boundary values. That's replicated here in the MATLAB code. So for ct1 equals 2, that corresponds to first interior node. This is the last interior node. And we solve the solution vector. We invert the matrix, U matrix, multiply it by the right-hand side, and that gives us all of these values all at once. Okay. All of these values all at once. And then move on to the next time step. And so on. But U value old gets overwritten by this U value new that we've just done. And then it can, okay. Run this code, see what happens. Same problem as before, so we should see the same answer. So here we can see the choice we've chosen gives us r is equal to 5. So r, for the explicit scheme, r had to be less than a half. Here r is equal to 5, so we're taking the time step 10 times bigger. So theoretically should be 10 times faster than the explicit scheme, because we're able to step forward in time much faster. Make an animation. If you want to advance size, I hope you see it. Happens very quickly. The whole solution happens much faster than and we don't have stability then. We have steps, and we don't do operations. Okay, let me leave it there because you guys can't see that particularly well. So it's the same animation as before, but we have to take much bigger time steps in order and return stability. So these codes are available to you on the website, or they will be from the CV. So have a look at them, run them yourself, play with them, try and break them. If you break them, come and tell me, and we'll try and figure out why they broke, and you might learn something from it. So go and play around with your initial conditions and the boundary conditions, whatever else. That's just okay, let's leave that. I'm going to go back to the slide just for a bit. We have about 10 minutes. So what I'm going to do is very quickly, let's go back here and I will briefly zip through one more of these. And I won't do the MATLAB code, but I'll make the MATLAB code available to you. Okay? So the wave equation. We looked at, remember there was three classes of equation. There's parabolic equations, of which we've studied. We came up with two solution mechanisms, the explicit method, the Pratt-Nicholson method. The wave equation is a little bit different. It's a different class of equation. It models physical wave propagation, wave vibrations. The one application may be vibrations of a musical instrument string. Okay? So displacement from a mean value. So again, let's imagine the velocity of propagation v is unity, and the spatial range is 0 to 1, just to make life a little bit easier. This equation to be solved, therefore, is the second derivative with respect to time is equal to the second derivative with respect to x. It's different from the last one. The last one had the first derivative with respect to time was equal to the second derivative with respect to x. That was the parabolic equation. This is the second derivative with respect to time equals the second derivative with respect to x. Again, we have an initial value. So at time t is equal to 0, we're given the value of mu. So in this case, we can think of it as an initial displacement. We can imagine a guitar string. Time t is equal to 0. Perhaps you're pulling the string. It has an initial displacement. You're pulling it, so maybe it's displaced at a maximum center of the string is equal to 0 at the end points, because in a guitar string or end string they're physically connected. So we have an initial velocity, because you let go of your guitar string, or your violin string at a certain initial velocity. Every point has initial velocity. And we also have boundary conditions. So at the ends of 0 and 1, we specify the values of u at these points. So very often these are because stringed instrument, they can't vibrate at the two end points, so they're usually set to 0. Everywhere else in bed. We do the same thing as before. We take the space dimension, divide it with step h. We take the time dimension, divide it with step k. We take a central difference approximation to the time variation on the left-hand side. We take a central difference approximation to the spatial variation on the right-hand side. On this time variation, we're looking at values of u at time I plus 1, and I minus 1. On the right-hand side, it's a spatial second derivative. So we're looking at, for a given point, for a given time step I, we're looking at spatial points n plus 1, n, and n minus 1. Okay, as before, h is the increment in position, k is the increment in time, etc. And we can rewrite this as an explicit calculation. Because on the left-hand side, the right-hand side, let's say we have all the values at time step I. That means we have all the values on the right-hand side, because everything here is in terms of time step I. On the left-hand side, we're trying to get from I to I plus 1, so the first term we don't have. The next term we do have, it's time step I, which we have. And if we have time step I, then we have the third term on the left-hand side, time step I minus 1. If we had I, we must have I minus 1. We have to go through all the intermediate. So we have everything in this equation is known to us except un I plus 1, and we can rearrange therefore and get an explicit solution mechanism of this. Where R is equal to k squared over h squared. Okay, so R is just we multiply across by k squared and end up with this R term. So we can rewrite the equation on the top, become the equation on the bottom, and this is an explicit method because at time step I plus 1, we can step through all the spatial points n, one after the other, and in terms of previously known on the right-hand side, information from the previous two time steps, put it all together and systematically update all the spatial points at time step I plus 1. So it can be shown that this is stable for R less than or equal to 1. So let's choose R is equal to 1. It simplifies the formula. For R is equal to 1, the formula becomes a little bit simpler. It becomes this. we have a very simple explicit updating scheme. You can step through all the n values at time step I plus 1 and just rewrite it in terms of information from the previous two. Here's a picture, a schematic. We want to fill in a given circle on time step I plus 1. We use information from time step I and in terms of time step I minus 1. Can someone tell me a problem with this? This looks very easy. Of you bright people, I've only got 5 minutes left. Can someone impress me? Last 5 minutes, you've done amazingly well. You've got 3-hour lectures, 2-hour lectures, nobody's falling asleep. There's 5 minutes to go. Impress me with an amazing observation in class. But just let me leave my last lecture this year able to say, my God, this class are so smart. And I go to the head of school and say, you should have seen what is it 6 on Tuesday, what they were able to spot. Someone spot something clever for me here, there's a problem. To get to I plus 1, we need I minus 1. What's our problem? Okay. Head of school. Yes, that's the problem. We need information not from just the previous time step, we need information from the previous 2 time steps. If you look at our little diagram up here, where's it gone? Where's it gone? Where's it gone? Where's it gone? Come on. Listen, what we're given is time step I is equal to 0. We're given all these green dots and the orange dots. And for the parabolic equation, that was enough to get us started. We could use the green dots and the orange dots to fill in rho I is equal to 1. But for the wave equation, we don't have them because to get to need I is equal to 0 and I is equal to minus 1. We need information from negative I. So getting started in the wave equation is which makes it different from the explicit solution to the parabolic equation. There's a simple trick because you'll see in the wave equation we're also given information not about the initial value of u, we're also given information about the initial velocity. How does that help us? We know that we can make a central difference approximation to the velocity time step 0. And we don't have information un minus 1 given to us. We've got information un 0 given to us. We're trying to get un1 time step 1. We're trying to get this thing started. But we need information from our equation required that to get from 0 to 1, we needed information of 0, 0, and minus 1. We didn't have this. So we can replace this term here, the last term in this equation, with this stuff here. And you put that in, this is what you get for your first, the all-important first step, get going. Okay? You can get going using this. We estimate information about u at the negative time step by using information about the velocity at time step 0. So this is a bit of an approximation, but it's okay, it gets us started. And from then on, that allows us to get time step 1, and then on it's easy, because then we've got time step 0 and 1 is used to get time step 2, 1 and 2 is used to get 3, 2 and 3 is used to get 4, and so on. And we can rearrange that, and we have a nice explicit method for un1. Time step 1 can be filled in sequence every spatial times one after another. Very good. Okay. There's a piece of code. I won't run it now because we're out of time. But there's a piece of code available on the net for the wave equation. It solves this using exactly these equations. Run it, play with it, break it, try and understand it, and email me any questions you have about it. Okay? Okie dokie, thank you very much. That's the end of all the lectures. Thank you, NUIM. Thanks for all your attention. And I shall see you on, when I see you next, I'll see you on Friday. I'll see NUIM, I'll see you on Thursday. And I shall see you guys on Friday, okay? So have a nice few days.